Here we will cover structured numpy arrays, but not too much since we will use data frames in a couple lessons. These are covered, which data frames are covered in the pandas library, which uses numpy as its base. So everything that we've talked about so far, uh, this numpy specific will also carry over to the pandas library. So that's a good thing. After we get finished talking about or just sort of introducing what a structured data array is in NumPy, we'll do some linear algebra things in NumPy. Then we'll cover a couple of the unique. I know you've already seen that, but you'll see it sort of a different way of using it. And I guess I should have put some parentheses here. We'll talk about cloning. So there's the dot copy method in NumPy, and then Ravel. Let's kind of see what those do. And then later, the very last thing that we'll do is we'll cover step functions the NumPy way. So we want to do this. I want to produce this function that's x when x is between 0 and 3, and 6 minus x when we're between 3 and 6, so that it kind of goes up and goes down like this triangle. And so we'll produce this guy, I think maybe 2 different ways when we get over here to Spider. Okay, so that's what we want to do. Let's go ahead and knock it out. So this is the video 14.3. And you can kind of see some of the things we're going to do in here. I've included some of the stuff that we did last video, so I'm just going to include it. And then I've created this data is equal to np.0, so it's putting zeros everywhere. You have to know. So the weird thing about the structured data types is you need to know how many are going in at first, and it's very difficult to put stuff in after you sort of claimed that there's 6. So in here you'll see. So there's 6 of them, and then the way you populate this thing is maybe you say data group group. So this is the group that sort of went with the last things that we did. Maybe that was 1, that was 1, that was 0. Where the zeros and 1, I think the zeros represent the ones that were the smallest. 0, 1. Right, so I'm putting that in as our group, and you can tell it what. So this is the names. So it's group X, Y, and F, and the formats are this U10 is UTF. So this yeah, it's in what the U stands for, Unicode, I believe is what it is, but it's in the Jupyter Notebook. So go check that out. So it talks about what that U stands for. I believe this is a signed integer 4-bit or a smaller version of it. I think it's maybe 4 bytes, then 4 bytes here, then 8 bytes for this floating point number. So X and Y and F are used in order to be able to populate this structured data type. So the next name is data X, right? So if you want to put that in there, it would just simply be our XY that we had above. And I want all the rows in column 0. So that's going to be my X. So this gives you a little bit, I guess, a better idea of what actually the data that's coming out, right? So before you had to know that column 1 represented the X coordinate, and here you can actually give it a name. Y is equal to XY, everything in XY, comma 1, F9, and then data, let's see, what's the last one? Oh, F, so we want to evaluate it, so F of XY dot T, remember you got to do the transpose because it's expecting column vectors in there. And we get that, and then let's just print data. I don't know, let's see what it looks like. Print data, and you can see the tuples. So now I have 1, 2, so I have 6 tuples in here, and it has a 1 for being the group that it's in, and then the 1 represents the X and Y coordinates. So that'd be the X coordinate, the Y coordinate, and then that's the function value, right? So 6 came out of that one, 0 came out of that one, negative 90 came out of that one, and so on and so forth. So this just represents sort of a different way that you could possibly use NumPy in the future. So what's the power of it? Let's do this. Print data group So now you see all the, so this could be names, this could be whatever you sort of wanted it to be. Maybe you got a print data x. So you got all the x's, and we could change that to be f. You get the function values and so on and so forth. This sort of gives you a sneak peek into what data frames looks like as well. And that's really the reason why I wanted to introduce this, is because that, I mean, the pandas library is how we're going to do data frames, and data frames uses this kind of idea. I mean, this sort of way of putting data together. You're going to have columns that will have these strings, and you can hit it other ways as well. So you look in the Jupyter Notebook, and there's another example in there as well. If you wanted to get out, I don't know, data group is equal to 1, no, 0. I think that's the one that has the small ones. And suppose that I wanted to get out, I think this is really the hard part of this, is how do you get out the x, y values put together? I can get out all the x values where, let's go data, we'll do it. We can do either one. We can do this one. So C, so I'm going to put this inside this guy. So this will give you this Boolean mask, right? So it'll go into here, and it'll only do the ones that are true. So F9. So you can see the x values that correspond to the -3 to the group 0, and then we can do the same thing with Control C, Control V with the y. So the x value -3, y value -5, these two go together, and these -2, -3 goes together. So that's my min group, if you will, if you remember from last video. And I mean, we can do IDX is equal to np.where data is really equal to 0, right? So you can get the indexes for all those, and you can just do so you can see that it's 2 and 4, 0, 1, 2, 3, 4, right? So it all lines up. Again, the issue here is sort of getting the information out and putting it together again. You would have to do some kind of maybe a loop or something different. It's just not as easy as a data frame to get stuff out of this structured NumPy data structure. So we will visit data frames later on, but this is to get you sort of warmed up with it. Okay, so now what we want to do is some linear algebra. And the linear algebra that I want to do is, the first one is matrix multiply, it looks like. All right, so let's just F9, and you can see the two matrices here. Matrix multiply matrices. All right, so let's do matrix multiplication. You guys are hopefully remember this one, np.matmul a comma b. It has to be the right order. I believe BA will not multiply. Oh, it does. Okay, so cool. I don't know. I didn't check that real quick. So that's a 2 by 3 and a, oh yeah, it did. I made sure that it would multiply either way. A comma A will not though. Okay, good. At least one of them won't. Okay, so we get that going for us. Another way to multiply two matrices is np dot, and I know that you might feel like, hey, we're giving you too many options. Np, let's see. Oh, there's another one. A dot b. This, it would also give you the same number. So 3 different ways of multiplying matrices, which none of them I like particularly. My favorite one is this one. So the 4th way is to do this, A times B. So why do I like that better than one of these? I don't think there's an easy way to maybe if you had A, B, and C. Here, let's do this. Let's set, yeah. So you would have to set C equal to this, and then if you wanted to multiply another matrix by it, you'd have to bring it in. I mean, in other words, I can't put comma A here. See, it doesn't like that. So that would, to me, that would be A times B times A. And if I can do that, let me make sure yeah, so it does work out. So you should be able to do A times B times A all sort of beside each other, and get it to come out. Whereas maybe you can do this one. So dot A. Yeah, this would work, but it sort of gets confusing. So they should give you the same thing. So A times B times A. It just doesn't look right. I mean, that's the best way that I think, without using this @ sign. I'm just going to use the @ sign from now on. So if you see me doing matrix multiplication, it's basically going to be with the @ sign. All right, about an inverse. So neither one of these two matrices are square. Let's do size A. I think it's A dot size. There you go, 6. A dot, what is the other? A dot, oh, shape is what it is. Okay. So it's a 2 by 3 matrix, and then B dot shape by 2. So that's good. And then if I would have done this, you could have seen that, you know, those would multiply together and these multiply together. So it doesn't matter which direction. Let's go ahead and throw a square matrix in there. So C is equal to np dot array 1, 3. I'm just making this up as I go along. Hopefully it comes out to be invertible, but it doesn't matter if it's invertible if you do the pseudo inverse. So F9, np dot array. Oh, I didn't give it the nested part. All right, and then C dot shape 3 by 3. All right, so let's do a couple inverses. Let's go A dot P. Linear algebra is what you get. So linear algebra dot NP. There it is. The NP dot linear algebra dot P inverse. You guys, hopefully you saw why I knew that wasn't going to work. So C F9. So that is, how do I know that's the inverse? I'm going to call it C inverse equals F9, and then I'm going to do C times C inverse. Not oh, I was using the wrong one. The @ sign, right? That's matrix multiplication. You can see that the ones are all down the diagonal, and then these are basically, all the other numbers are basically 0. So something times 10 to the negative 16th is pretty much 0. And if I do C inverse times C, oh, I did the wrong times. Just talked about this, right? All right, so then you get ones down the diagonal, and every other number is basically 0. All right, so that's how you get an inverse. Suppose we wanted an inverse of A. So A dot NP dot linear algebra. And so make sure you use P inverse. It's a pseudo inverse, and it can be calculated even if this is not a linear. All three of these are linear independent. So A F9. So that's a 3 by 2, and then 3 by 2. What was A shape again? A 3. So can I multiply this one by this one? 3 by 2. Yes. So this would be times A. Yeah, that's not good, right? So in linear algebra, pseudo inverse. Let's see, maybe it's oh, that's right, it's the other way. So the pseudo inverses have to be multiplied a certain way, and it just so happens that this one's there. It's on the left-hand side. So A times the pseudo inverse gives you 1 to 1 and then 0s in the other one. Okay. So technically, you could get an inverse but there's going to be a left inverse and a right inverse, and the pseudo inverses. Make sure you go back. Well, I don't know if we covered the pseudo inverses as much as we could have in our linear algebra class, but you can go back and read about those bad boys. Okay, so let's just go. Let's say A is equal to np dot array. I'm going to give a real simple system of equations here so we can see how to do that. So I'll give one that's like maybe 1, 1, and 1, 2. Let me solve this thing in my head real quick. B better equal np dot array. Maybe 5, 8, 7, 7. And those two together, I want 3, 5, and 7 would be 12. 3 divided by that. Okay, so yeah. All right. So now I want to do np dot linear algebra dot solve. And there's a whole bunch of things. You can do SVD, you can do tensor. I mean, you can do lots of stuff here. We're going to do solve here, and it tells you down here, right? So A and B, it tells you what to do. And then F9, oops, I didn't. Then 1 and 4. So does 1 and 4 work? 1 times 1 is 1, plus 1 times 4 is 5. So that gives us our 5. And then negative 1 times 2 times 4 is 8. 8 minus 1 is 7, and 7. Okay, so you can see how to solve systems of equations very, very quickly using either the inverse. You could absolutely use the inverse in order. So let's just use the inverse. Of course, I have to do that. So it's np dot linear algebra dot, and there's another inverse in here too. Just inv, and A is definitely going to have an inverse. And then times B. Should get the same number. Yes. Okay. Good. All right. Other helpful commands. If you were to be given an A that looks like this, and maybe we want to replicate it. So I want to have set B equal to A. Let's see. A and B are right beside each other. So you can see it's a 12 by 2. What I'm going to do is I'm going to change the 0, 0 element. In other words, I'm going to change that -1 to be negative 10,000. And the only reason I'm doing it so big is so you can absolutely see what happens here. But note what goes on right here between these two when I just put A equals B. This is an alias. If you remember what aliases do, if I change B, then it's also going to change A, but that might not be what you want to have happen. You can see that, right? It changed. So now we need to figure out how to clone it. So let me redo this, redo A, F9, change it back to what we want it to be. And if you want to clone, you're going to have to do B equal to A dot copy. F9. All right, so it sort of looks the same right now, but if you took this one and ran it again, F9, you can see that only B changed that time and not A. So it doesn't point to the same memory location like it did last time. All right, let's see here. Let's print A. So print A. There are some repeats in here. Suppose we don't want these repeats to occur. So there's 12 of these suckers, and I can't find one right now. I'm sure there's a couple. -1, 0. Oh, there's one. -1, 1. So that's a repeat. So -1, 1, and -1, 1. 0, -1, and 0, -1. Suppose we're just interested in just finding the unique versions of that. So that A1 equals np.unique. Now, if you just run it like this, it's going to just give you out, it's going to unravel it. We'll talk about ravel here in a second. But it's going to basically, let's see what it does. So A1 is just equal to all of the numbers uniquely in it. See how it's -1, 0, 1, and 2? So those are the only unique numbers in that whole matrix. That's not what I want to do. So let's change this to be axis equals 0. So by rows. Let's see what happens then. So if I did that, then you would have so these are all unique or XY coordinates, if you will, if that's what you had in here. That might be something that you're interested in. So 1 F9. So all it did was it took out the repeats. So that's what unique does. Pretty neat little function. Let's see, A1 dot ravel, I'm going to show you what ravel does. So I think of this as unravel, but for whatever reason, whoever programmed this called it ravel. But if you unravel this matrix here, it would be -1, -1, -1, 0, -1, 1. So it would be this one-dimensional numpy array with all of the numbers that are in there, and that's what it is. And if you did a.ravel, it would do the same thing. And sometimes you're going to need to be able to do that, so just know that that's there. And the only reason I gave it to you is because I needed it one time. I think I had a picture, and I was trying to do something with every single element of the picture and then put it back together. So you could do a reshape would work as well. You could absolutely do reshape on there, but if you just didn't want to worry about that, Ravel will do it for you as well. All right, so our last step here is to remember what we were trying to do, create this little function here that does that. So let's go back, and what I've done is, so I've given you some x values. So if you hit F9, that's 100 numbers between -1 and 8. I'm not super concerned what they are, but it just broke it up evenly into numbers, into 100 numbers between those two. And then I'm giving you two different ways to define the function. So if you look here, it says, well, I'm going to use this is the function that I'm using, and these are the Boolean values that we're multiplying by. If x is greater than or equal to 1, then that'll be a 1, and I'm multiplying that by, if x is less than or equal to 3, it will also be a 1. So 1 times 1 gives me 1, and that's really not doing anything, and then it's multiplied by the function that I'm worried about. Same thing over here. If you do 6 minus x, again, you can just keep however many conditions you want to put on this thing. You just kind of keep going and keep multiplying them. In this case, we want x to be greater than 3 or less than or equal to 6, and so that's how g will be defined, which is the same thing as we did down here. Down here, if you try to do this inside the lambda function, it won't vectorize for whatever reason. I haven't really studied it, but it came back with some a.ne, blah, blah, blah. So I just didn't worry about it, kind of putting them together. I just took them apart and multiplied them because I want both of these to be true. And that's why you can take them apart and multiply them. Same thing here, just took it apart and multiplied. That's this piece. So this is the function, and that goes with that one. And all I want to do is I want to define both of these, and then I want to test it. So the reason why I said that the Python way is that we want to use this now to time it, right? So there's this function, and I'm not sure if I've introduced this yet. I don't think I have. I'm sure you've seen it in the Python, in the Jupyter notebooks somewhere, but I'm going to just time this, and it tells you how quickly that it takes to evaluate. So again, that was 100 numbers inside, and it's doing that first one, this one right here, where I created this list, and then I went through each element of the list and appended the answer to the list, and then returned a numpy array for that list. So that's what I did here. Here I just defined the function. And now I want to do, but I defined it so that it could be vectorized. So this is the vectorized version of g of x, and let's see how quickly this one gets done. Oh, the other thing is if you use this percent stuff, Spider doesn't like it. So just know that anytime you use any kind of percent, these are like magic functions. Anytime you use those, it's just not going to like it. So just know that going in. And you can see 379 divided by 701. I have my calculator here. How much faster is that? So 379 divided by 7.01. And we are about 54 to 55 times faster than if you would have. So this function, this vectorized function up here, is much faster than trying to create your own little way of doing business. To 55 times faster. So that's a lot. If you're doing a whole bunch of things, then you want to definitely use. So if there's a whole lot of data, you definitely want to use this vectorized version. All right, let's run this, and you can see that this plot kind of looks how we think it should look. All right, that's really all I got this time. I hope you guys got something out of it, and we'll talk next time.